Friendly reminder, as you can see on the calendar, that your homework on Chapter 29, homework 13, which is just on Chapter 29, is due tonight. Again, that's because there's an exam Friday, so that you have time to study the solutions. But that has been open for over a week now. There's a lot less questions on homework 13 on 29 than normal because that's all it is. So if you this is all new news to you, you don't have to freak out as much. But it is due tonight. All right. Today I'm going to spend a few minutes on the one last topic I didn't get to last time, polarization. And then we'll review everything else. Polarization. I've mentioned a few times that there's one thing, let me say it another way. Everything we've talked about so far applies to all types of waves. What are the two types? Longitudinal and transverse. Good. So everything worked for them. Refraction, diffraction, reflection, dispersion, where they spread out. That was the colors in the rainbow. Interference, superposition, Doppler effect. Remember all that stuff? This is the one that only works for transverse waves. So transverse only. Polarization. Polarization. The reason this only works for it will become clearer, but transverse, remember the disturbance might go up and down vertically, but the wave looks like it's going sideways. It's perpendicular or transverse to the wave motion. Because it's like that, you can block wave motion in one of those directions. That's what polarizing a wave is. So here's a typical wave of light, because light's a transverse wave. Do you remember it actually has an oscillating electric field and magnetic field? I gave you a picture. It increases in one direction and then the other, and then up and then down, and then up and then down. The electric field's changing. Likewise, there's a magnetic field associated with it that does the same thing, perpendicular to that. It's coming in and into the and back behind and then back out and into the board. So it's going this way. Polarization has more to do with the electric field, so we'll just look at one. The electric field. So the way I've drawn this wave would be polarized. The electric field goes up and down, up and down. So if you're looking at it like this, head on, you just see it in this plane, the plane of the board. Or if you look at it over here, it's in the plane of the board. You with me? This would be a different plane. So this would be a polarized wave because it's only oscillating in one plane. It's polarized. Most light isn't polarized though. It can vibrate in this plane, it can vibrate in this plane, this plane, this plane, this plane, this plane. All of them. The lights coming out of the above ceiling lights are non-polarized. That means they look like this. Whoops. If this represents the planes of the electric field, they can oscillate in all kinds of planes. This is unpolarized light. That's what's typical. How does it become polarized? Some of these planes must get absorbed or blocked. It's the electric fields. How many of you have a pair of sunglasses? How many of your sunglasses are polarizers? I'm like, if I'm going to have sunglasses, there's no other way to go in my mind, because polarizers are cool. So these were lost and found, but they're polarized. What does light do when it goes through them? Here's a polarizer. It comes in, and I'm not holding you to this, but the brain lapse. Molecular chains in here are aligned in one direction more than another. And so the electric fields on some planes get absorbed more than the other ones. It's basically the molecular structure and orientation in the material itself absorbs or transmits the electric fields depending on the plane. So essentially it blocks all but one direction. So here's a model. If this is a polarizer and the unpolarized light's coming into it, which ones make it through? Well, only the one that's vertical. So on this side, all you get is polarized light. Yes?
So in some sunglasses, are there some that are more polarized than others, and have like a smaller amount?
No, pretty much all sunglasses are polarized the same amount. Yeah, they do this. It's kind of like all or nothing. I don't know of any that do it that way. So this is polarized light. So what's fun is you can send it through a second polarizer, sometimes called an analyzer, because let's analyze this light. What will happen if it tries to get through that second one? It gets polarized. Can it make it? Sure. So this is like it has no effect. You see the same light over here. What if, though, you turn the second polarizer perpendicular to the first? It blocks it, and you actually see nothing. This absorbs this plane, and so it blocks it. You get no light. So you started with unpolarized. It gets polarized. And then you can block it or let it through or somewhere in between. Some gets blocked. You can partially block polarized light because only the vertical components of this get through. Some of these have a vertical component. Let's do that for real. But again, that's what polarization is. That's what I'd like you to know. And it only works for transverse waves. Make this higher. There we go. So there's unpolarized light. I'm going to stick a polarizer in the way. This tells me that it makes it polarized vertically, like we just did. There you go. Doesn't look much different, does it? You can't tell. Notice it's a little dimmer. Well, it should be. I'm blocking some of the light. Only the vertical stuff gets through. Let's take a second polarizer. If I have this white tape up top too, then this one is vertical. It would be like this. They're both vertical. Should light make it through? Yep, makes it through. Now if I turn it though, watch what happens. It's like magic. So you can analyze polarized light. You know, if I look at it too, I see it. Now I don't. Right there. Disappears. Not where the light's at. I see you guys, all the other light, but the light that's polarized right here, nope.
What's the benefit of having polarized sunglasses?
So what's the benefit of polarized sunglasses? And what do? They block polarized light, obviously. Where do you get polarized light? Some of you probably know from your gut why you wear sunglasses. You probably already know the advantages, you just might not have known what was going on. It's not the UV. They can have a coating to absorb UV, but that has nothing to do with the polarization. That would protect your eyes. That's a good thing. But these have that coating also. Did anybody wear sunglasses, polarized sunglasses specifically, for a certain reason? When you're doing something that makes it easier or better?
So I fly fish, and so when I'm looking at the water, like if I don't have glasses on at all and the sun's hitting it, I can't even see anything at all. So it's like almost not working.
So he fly fishes, and it's the reflection off the water. Glare. The reflection gets partially polarized. I'll do that next. Well, that polarized light, it's glary, duh. So you put on your glasses, and it blocks that polarized glare. Now you can see into the water. where the fish are at. It can block glare off of car surfaces. I can see it, the light is reflecting off those seats. Whoop, not blocked, blocked, not blocked, blocked. It gets rid of glare. It can do it, photographers use polarizers in the front to get rid of glare. Fall foliage can look deeper and richer colors if you can block the polarized glare off of the leaves.
Like if you're skiing, they block reflection off the snow?
Yeah. Reflections off of most non-metallic surfaces is partially polarized. So let's block them and you can get rid of that glare. So let's see if I can do this. I have a piece of glass I'm going to bounce the light off of. There, see, it reflects up. Can you see that okay? There's my head in the way. Well, now I'm going to take a polarizer and see, is that reflected light polarized? Oh, it is. Look at that. Not in that direction, but it is in that direction. I'm rotating the... Where's that? There it is. I rotate. So it gets polarized in the horizontal direction. Do you see the tape on this? This is vertical slots. It doesn't get through vertical. So that's saying the reflected light got polarized horizontally. Looks like this coming to the screen. It got partially polarized. So your sunglasses do this. Block the glare. If you turn your sunglasses this way, you can see the glare. It makes it through. That's how I test if lost and found sunglasses are polarized or not. Or if a store is trying to gyp me. Just hold them up. Look at some glare. Don't see it. Now I do. Don't see it. Now I do. They're polarized. If it's always the same, they're not polarized. Quick down and dirty way. Or get a second pair and do this. All right. Oh, you disappeared. Can you see my eyes? Of course, you probably can't see them anyway, but I can see you. I can't see you. It blocks the light. You can come out and try it afterwards if you want. One more quick thing here with, all right, light gets through. Let's make light not get through. Stresses in things. Sugar molecules can change the orientation of the polarized wave. So if it comes in polarized vertically, after it passes through this, it might come out at a slightly different angle. Or the sugar molecules might rotate that plane a little bit. And each wavelength, each color gets rotated a little bit differently. So it's fun. If you have a setup like that and you insert this, let me get on this side. Light makes it through. And you see different colors depending on the angle. Let's try the sugar molecules. This is corn syrup, by the way. And if I rotate the polarizer, I can change the colors that it blocks. Again, it's because the sugar molecules are rotating that plane of polarization, transverse waves. My favorite, though, are my glasses. Let's get a bigger. Close enough. Architects can use this to analyze stresses in the materials, because stresses, the tension inside, can change the polarization. You know what? I guess it's not in focus. That's the problem. You can't tell as well. Well. Okay, that didn't show up as well on this. But you can actually see light and dark spots where it gets through and doesn't. If you just hold them up and I do it, works like a charm. You can come down and try it. Or two pairs of sunglasses. You can do the same thing. Just put one on and hold the second one like this. Sandwich something in between and you'll be able to see it. Questions about polarization? So it's when they're perpendicular, nothing gets through. Then I'm going to ask you 3 clicker questions to help review this chapter 29 stuff, and we'll continue reviewing the rest of it. All right, there's the first one as you log in. So diffraction is that bending of light waves, well, any wave, as it goes around an edge. It's more pronounced. There's more diffraction. There's more spreading. For which of those? Oh, right. I didn't click it. Thank you. There you go. Now you can actually respond. I'll even give you a hint, because it's a way of review. Answer C, one medium to another medium. Is that diffraction? What is that? Refraction. Good. That's when you change mediums. And what happens when you change mediums? It refracts. Why? The speed changes. Very good. That actually happens. Remember, that's how you can see. When light changes from air into your cornea, the front of your eyeball, it changes mediums. It slows down, it bends, it refracts, and that's how you're able to focus and see something. All right, 10, 9, 8, 7, no hollering, 5, 4, 3, 2, 1, 0. We got 53 votes. 85% through small openings, correct. It's harder to get through, so it's going to spread out more and be more pronounced. Questions? Concerns? When light undergoes interference, the quantity most affected is what? Is it the frequency, the amplitude, the wave nature, or its phase? Light waves can superimpose, they superposition, but they can interfere constructively or destructively. They can add together or cancel. What's actually changing about that wave, in this case light? What quantity is most affected? Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. 79% of your amplitude. That's right. If they add together, the amplitude gets bigger. If they cancel, subtract each other, it gets smaller. It's the amplitude. That's the yeah. With like this wave, that's the amplitude. The displacement from the equilibrium position. So if this was light, it would get brighter if the amplitude increases. If it's sound, it gets louder. If it's water waves, the waves get higher. That's the amplitude. Look at it this way too. If it's light, it can interfere. It either goes dark or brighter. It doesn't change color just because of the interference. If it changes color, the frequency and wavelength must have changed. Because it's light. The velocity didn't change. Now one more. A beam of white light that reflects from a pair of closely spaced surfaces. So like you have a front surface and a back surface, and if they're close together, we often call that a thin film, like a soap bubble. Or gasoline or oil on the top of a water puddle. It makes a thin film. So you have two surfaces close together. You can see some color out of those in the reflected light. What makes that color? In nature, there's a lot of this happens out in nature. You'll see colors on things. Butterfly wings, beetle shells. Actually, actual shells, like from the beach, from the ocean. There'll be a thin film on the shell. You see colors. What are the colors you usually see the most? I mentioned this. The iridescent colors, which are more of those secondary cyan, magenta, and yellows. Next time you look at a bubble or gasoline on a water puddle or something, they're usually most often the combination of two of them, which are the secondary colors. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. At least we got the same number. 85% C. Very good. Very good. You subtract the color out, you're left with the other two, hence the secondary colors. For a soap bubble, what subtracts a color out? It bounces off the front, but one goes through and bounces off the back. When they come together, why would one disappear? It's like two waves coming to your eye. Why would they cancel? Interference. If they destructively interfere, that color is subtracted out. All right. Before I go off, what are your dying questions? Anybody in your preparation and your studying that's still confusing to you? Yes?
Can you show us like the formulas we need to know?
Formulas. Let's see. Just going through my notes here. Have you guys realized there's a summary at the end of each chapter that lists formulas? Yeah. That's a good place too. There aren't that many at this time. For a pendulum that swings back and forth, we had the relationship of the period was 2 pi times the square root of its length and gravity. Do you remember what period is? That's the time it takes for one oscillation. So it tells you how long it takes to swing back and forth. It's based on how long it is. If it's longer, it takes more time. But if you accelerate it greater, it'll go faster, like if you moved it to Jupiter. Do you remember that lecture? That was weeks ago now. That was one. G is the acceleration due to gravity. T is the period. Yeah, it doesn't do any good to just have formulas if you don't know what they mean. L is. is the length of the string. These are relationships that guide our thinking, which tell us what I just said, that if L is longer, it takes more time to swing back and forth. If you move to Jupiter where the acceleration due to gravity is larger, it'll accelerate faster, back and forth in less time. What's the source of all vibrations? I'm on this page, so I'm going to... What's the source? What's the source of all waves? A vibration. Something's got to be vibrating. See, how is frequency related to period? Inversely. Good. What's frequency measured in? Which is an inverse second. Cycles per second. Cycles per minute. Rotations per second. RPMs. Revolutions per minute. That's a frequency. That tells you how fast it goes back and forth. The rate. Because you say fast, you don't know. Do I mean frequency or time? Frequency is the rate. Period is the actual time. How are both of those, well, how is frequency related to wave velocity? These are how fast it vibrates back and forth, the rate or the time. Source of all waves is a vibration. That's a vibration. It can create a wave, and that can travel at a certain speed. How is frequency and wave velocity related? There you go. Wave velocity is wavelength times frequency. Again, outside of this class, you might see that as the Greek letter lambda is more common. I've just been using W to keep things simple for wavelength. But lest you're confused, same, just different character to represent the same thing. So with this, people got confused. All right. Tell me what's different about law versus law. Okay, amplitude. Let me redo it then. I'll try to keep the amplitude the same. Law. That was beautiful. Law. Are they about the same sound, loudness? That would be amplitude. So they have the same amplitude now. But what's different? Frequency is different. All right. If the frequency is different, this one up here, that's a higher frequency. What else do you know? The wavelength must be shorter. Why? Because it's traveling to you at the same speed of sound. What's the speed of sound? Speed of sound in normal air and conditions was about 340 meters per second. That's how fast the wave travels to you. But what's the air doing in between us? It doesn't wiggle? I know what you mean. It doesn't, this air doesn't travel over to your ear. The air stays put, the net effect. But this air gets smushed, compressed, and spreads out. Hits its neighbor, domino effect. It's those interactions. It's a mechanical wave to travel through. So the wave is vibrating at, say, oh, I don't know what this frequency is, how about 700 hertz? It goes back and forth 700 times a second. But the wave travels to your ear at 340 meters per second. And down here, it's a lower frequency, so it's a bigger wavelength. If frequency decreases, the wavelength increases for a wave that's traveling the same speed. Same with light. Same with AM and FM. Radio waves. Are radio waves transverse or longitudinal? A radio wave. It's an electromagnetic wave. It's part of the electromagnetic spectrum. It's a transverse wave. It's a form of light we can't see. A radio wave. That's how the information gets to your device. Now your device has a speaker and plays sound. What kind of wave is that? longitudinal. So a sound wave is not the same as a radio wave. Make sense? A radio wave, electromagnetic wave, doesn't need the medium to travel through. The interactions actually slow it down. For a longitudinal sound wave that needs the medium, that's how it travels, is the interactions. So the greater the interactions, the faster it goes. There's a formula. Beats. What are beats? Right? Wee wiggy. What are beats? Interruptions of sound is because waves are interfering. They're out of phase. So we have constructive and then destructive. Are they always out of phase? Yeah, it's like they get in phase and add together, and then they get out of phase and destructively interfere. In phase, out of phase. They go in and out. If you looked at one, if you had this wave and it interfered with this wave, what would happen? Constructive. See how they match up? When this one's up, that one's up. When this one's down, that one's down. So they would add together and be a bigger wave. Constructive interference. Destructive would be, see how they're opposite now? And you would get nothing. So a beat goes, they add and then they don't. And they add and then they don't. And it would look something like this. And then they don't. And then they do. And then they don't. And then they do. What do you hear? Wah, 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 wah. That wah, 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 wah. Faster beats. That's the wavelength of the beats, not the smaller little waves that are at it. That's what you hear, that wave. And the actual frequency you hear, the beat frequency is the difference between the two smaller ones. So like if this is F1 and this is F2, as they go in and out of phase because they're slightly different frequencies, you'll get a difference that you hear. So if you had 500 hertz and 510 hertz, what's the beat frequency? 10 hertz. How could I get a beat frequency of 10 hertz another way? That's right, 490. You would hear the exact same wah, 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 wah pattern. You wouldn't know if it's higher or lower just from that. But you would know it's 10 away. I think that might have been the last formula. Yeah.
Question about
Laser to the moon. Get back to. Alrighty. I off the top of my head don't remember the question as well. Let me see. Well, it's right here in theory. Remind me, is this the current one or the one before? Yeah, okay, that sounds better. What number is it? $10? Nope. There, 12. All right. How long does it take a pulse of laser light to reach the moon and bounce back to the Earth? And it gives you the Earth-Moon distance. Okay, we have to go back to the beginning stuff. What is velocity defined as? Distance over time. It's the rate that you change your position. It's the change in position over time, how far you go versus time. It hasn't changed. That's how we got that formula. Wavelength's a distance. Frequency is over time, 1 over time. So, how fast is the wave going? It's the speed of light. How far did it go? To the moon and back. So you just solve for t. That's kind of cool. That's actually one way they measure the distance to the moon and monitor how far away it is from us. They measure the time it takes for a laser to go off the moon, off a retroreflector, and come straight back to where it came from. They just time how long that takes. Now you know this one. We know the speed of light, and I know how far away the moon is. Well, twice that distance. They divide by 2, and there you go. That's pretty cool. Good. Any other dying ones? Or non-dying questions? Well, I'm looking at the exam. Let's see what else I should tell you. Oh, do you remember the labeling of waves? All the parts? What's this line called? Equilibrium position. What's this bump called? Crest. Trough. How about the spots where it crosses the equilibrium position? Those are the nodes. Place of no displacement. Nodes. What are the maximum displacements called? Antinodes. What's this whole wave form called? We did it with a spring. We'd make these. We hit resonance, and they'd reflect back on themselves. Standing waves. Yeah. As I drew it here, it creates a standing wave. And we had one that looked like that. We had another one that looked like that. Oh, that was beautiful. But anyway. There we go. Whatever. Doppler effect. What's the Doppler effect? That's on the test. What is the Doppler effect? Uh-oh, you guys are in trouble then. There's a change in frequency. Remember the waves? If you just have a sound source and it emits waves, they spread out. So if you're over here listening, they hit you at a certain interval, frequency. They're yay spaced apart, wavelength. You can determine the pitch and the frequency if you measure that interval or the space between it. Side note, what if ripples in water come at you like this? Boom, next one, boom, next one, boom, and you know they're yay far apart. Let's say they're a meter apart. What's the wavelength? A meter. And they pass you every 2 seconds. What's that? Hey, now you know the period and the frequency. How fast is the wave traveling? There you go. You just plug it into the formula. But back to Doppler effect. If this or this are coming together, what happens to the waves over here? It's traveling that way. So they're getting smushed together. And so you hear it's a shorter wavelength, a higher frequency. The pitch goes up. It's higher. And if you're standing over here, as it goes away from you, that's the Doppler effect, the change in pitch because of the waves getting smushed together in it. What if you go faster than the speed of sound? Yeah, the object gets ahead of its waves, and you actually get a cone. You know, the circles are more like, this is harder to draw. Kind of like that. Yeah, now there's a bow wave. Just like your speedboat goes too fast. You get those wave fronts hitting you. It's the same with the water waves. It's the same with an airplane. And if you're right here, do you hear anything yet? No. What do you hear when that passes you? Boom! What do you hear after it? It's like you're back here. Kind of the Doppler effect, lower frequency. What can produce a sonic boom? Anything that goes faster than its own wave. Let me emphasize that. Anything that goes faster than its own wave. Yeah, because in water, it's the boat going faster than the speed of waves in water. So if the boat's going faster than the speed of the wave in the water. Note that what if the, I'm going to leave it at that. What do you think the pilot hears? Nothing. That wavefront never superimposes to his ear or her. What makes sound travel faster? This is the speed of sound. What can we do to the air in the room to make the sound get to you more quickly? Evacuate it? Then you wouldn't hear anything because it needs the air to get to you. And you weren't sure. Hotter or colder? Which one should it be? What transmits the sound? The interactions. Yeah, so if the molecules are moving faster, are there more or less interactions? More, so it'll go faster. Remember the dominoes? Where they were closer together, there were more interactions happening more quickly, more frequently, I should say. That one won. The wave went through those faster. So we could heat up the air. Yes?
Wouldn't in theory, if they're moving faster, the gas wouldn't not interact with much at all?
Yeah, there's two things going on. Because it's hotter as a gas, they move quicker, sound waves. The reverse is true with light. Because it's a gas, they're far apart. But let's compare. We started with air in the first place, a gas. We still have a gas. It's just a little hotter. They're jiggling faster, so they interact with each other more frequently. Sound goes through faster because it relies on those interactions. Light actually goes faster in warm air also. I mentioned this before because, see, it's confusing. Let's discuss why. Does it need the interactions? No, the interactions slow it down. So wait, shouldn't it go slower? No, because the gas, when it's hotter, expands. They get farther apart. And now the light can get through without interacting as much. The sound relies on getting one of those particles, making it jiggle, and that jiggle interacts with its neighbor. It relies on that. So if they're jiggling faster, that can go quicker. Light doesn't like the particle. It doesn't want them. It doesn't need them. It could go faster straight through. Hotter air expands, and so it's easier to get through. If it interacts with one of them, that slows it down, yes. But it's because that interaction slows it down. But the light doesn't need the interactions to get through. It doesn't need the particles. Because it expands, it can just whip through easier. It's like the crowded room is less crowded now. As the molecules heat up, they spread apart, and light can slip through easier.
So
Light actually has less interactions in hot air because they're further apart. So yeah, both go faster in hot air. And it's all about interactions. It's just sound needs those interactions. Light doesn't. Let's do another example then. So light in air versus water. Water, liquid, they're much closer together. It's harder to get through. It slows down in water. Sound, though, speeds up in water. Because it's a liquid compared to a gas. They're closer together. The dominoes are closer together. So they can bump into their neighbors more frequently. And so sound will actually go faster in water than air. Because it needs those interactions. There's more interactions. Light slows down because of those interactions. You have any other questions? I'll keep looking here. We did that, we did that, we did that. Diffraction. You got some wave fronts coming in, say in this direction, and you hit an edge. What happens to the wave front? Well, this one's not blocked, that one's blocked. Over here, it bends. You get so if I continue this, over here it kind of goes straight, but over here it kind of bends. It spreads out. That's diffraction. If you had a second edge, it does it over here also. And spreads out. What if you have a second slit over here? That one spreads out also. And see how they interfere? So you can get an interference pattern as they superimpose. Loud spots, quiet spots. We did that with two speakers. Two speakers. Two sources. We did it with light. We got the bright spots and the dark spots. What's it? Yeah, there's the slits. So sound waves diffract through them and can then interfere and have constructive or destructive interference. And so does the light. That pattern on the screen where you saw a bright spot, dark spot, bright, 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 destructive, 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 constructive, constructive, constructive. That's these waves overlapping. You answered in the clicker question, diffraction's greater when? If you make it harder to get through. There's two ways to do that. Narrow the slit, more diffraction. What else can you change? The frequency, and hence the wavelength. If your wave is smaller, it gets through easier. If it's longer wavelengths diffract more because they're harder to get through. Sound waves too, they diffract around buildings. There's an edge. Different waves diffract different amounts depending on their wavelength. Oh, you definitely need to know all the color stuff. How red, green, and blue combine, and if you subtract one of those, how they combine. You're free to put my T-shirt on your paper. There's Google the image or draw it or just write it out. It doesn't matter. But because I ask you ways to subtract colors through different ways. Remember, you can do it through interference. You can do it with a dye that just absorbs it. And if you subtract the color, what color is left? There's some questions like that. What color is being absorbed on my shirt? Red and green. They resonate with these. Their natural frequency, they're driving the pigments in my shirt. And if they naturally want to vibrate at that rate, they absorb them and resonate. Cause it to heat up. Blue doesn't like that. It reflects back off. Hey, we did pretty good. There's one question on polarizers. Go team. See you Friday.